Okay, so we finally get to start with some new material for our class. Unfortunately, the first few things we're going to do is really just learn some additional definitions. This video is going to seem really straightforward and simple, and what I'm going to ask you to do is to pay very close attention because it's really important that when we do talk about this kind of notation and these definitions that we are very, very precise in what we're saying. And so I'm going to be really nitpicky in terms of talking about it as best I can and also in terms of grading you. So there's going to be a lot of material here that you actually need to memorize. I hate memorization. I don't know if you love it or you hate it, but you're going to have to memorize it because you really need to know these backwards and forwards. Hopefully you learned about sets and intersection a long time ago. You need to understand these definitions in the same with the same automatic nature that you know the what the intersection of two sets is. On the class website, you will find a handout that is a list of things I really want you to memorize right now, and just go through that and memorize it. So let's start by defining a list. The book defines a list as a finite ordered sequence of 0 or more elements that can be repeated. And we're going to use the book notation for lists, so we're just going to use these less than, greater than signs to be brackets around a list. Here's a couple of examples of reasonable lists. Most important to note, of course, is we have a list called the empty list. And lists do have an order, so unlike sets, but very much like tuples, if we have the list A comma B, that is not the same as the list B comma A. So at this point, I hope your next question is, what's the difference between a tuple and a list? What makes this different from this? So the answer is that this is a computer science course, and there's actually a computer science difference between a tuple and a list. So this list here is actually very different from this tuple. And it's not that the difference is in the contents or in the order, but in fact in how it's represented and which parts can be randomly accessed. So if we have a tuple, and let's suppose we have a 53 tuple, so we have a tuple with 53 locations, any location in that tuple can be accessed in constant time. So if I want to look at the 23rd item in there, I can get it in the same amount of time as I can get the 52nd, at the same amount of time I can get the 3rd, no difference. With a list, we can only randomly access the head and the tail in constant time. So of course now you're asking me what's a head and what's a tail. If you're familiar with Scheme or Lisp or a language like that, you've probably heard of head and tail before. For those of you who are not, the head is just the first element in the list. So if we have the list R, comma, O, comma, W, comma, A, comma, N, the head is R. The head of this list here is 8. The head of this list here is the smiley face. The head of this list that only has one element with an exclamation point is just that exclamation point. The tail is everything else, and the tail is also a list. So the tail of Rowan here is the Owen. The tail of 8,6 is 6. The tail of this weird stuff is everything but the first weird thing. And the tail of this list that only has one element in it is the empty list. It's really important to remember that the tail of a list is a list. So notice that our notation again, remember I said we were going to be really nitpicky here. The tail of this list with two elements is a list with one element. It is not just the element itself, even if there's only one thing left. The other important thing to note is the empty list doesn't have a head or a tail just by definition. Okay, so now more definitions. A string is a finite ordered sequence of 0 or more symbols that are placed next to each other in juxtaposition. In other words, it's pretty much what you've always thought of as a string, a bunch of characters. In this case, we're going to call them symbols placed next to each other. An alphabet is a finite set of symbols, and we can use our alphabets to make strings. So, oh, and one more thing here. I may, if I'm trying to save space, if I'm doing this in the classroom, this is more important because I get lazy and don't want to write out the word alphabet. I may just use alpha beta. But occasionally here, if I want everything to fit on one line, I might write alpha beta instead of the word alphabet. Furthermore, sometimes I get a little bit lazy. I'm hoping not to do so on these videos. I'm trying to be very precise, but an alphabet, the official formal definition of an alphabet is that we have a set of symbols. I might say a set of elements, I might say a set of characters, I might say a set of letters. Really, we're talking about a set of symbols. So, for example, here's a set of symbols. They also happen to be letters in the English alphabet. And an alphabet is a finite set of symbols. This is a finite set of symbols, so A must be an alphabet. And here's some strings over the alphabet A. So we talk about a string being over an alphabet. So the string little a by itself, because it's in there, BBM, AABB, all of these strings can be made up of the characters in this alphabet. Here's some more examples of alphabets and some strings that you can get out of them. Alphabet is A1 is this weird thing, A2 is this, A3 is this. So these are all alphabets. How do I know they're alphabets? Because an alphabet is a finite set of symbols. These are all finite set of symbols. Now, there may be an infinite number of strings that you can come up with over an alphabet, but each individual string is just a finite sequence of symbols. So if we just have the string A, that happens to be a string over the alphabet A1. It's also a string over the alphabet A2. It's also a string over the alphabet A3. But if we look at this weird thing, that's a string over the alphabet A3 unioned with A1. Is A3 unioned with A1 an alphabet? Well, what's an alphabet? An alphabet is a finite set of symbols. A3 unioned with A1 is a finite set of symbols, so this is a perfectly valid alphabet, and there's a string over our alphabet. We're going to use the Greek letter lambda to represent the empty string, and we're just going to say that lambda is a string over any alphabet. The length of a string will define to be the number of elements in that string, and we're going to use absolute value bars to represent that. So if we want to know what are the lengths of these different strings, it's generally just the number of symbols in there. Of course, the length of lambda, the empty string, is in fact 0. Remember, these are all strings over an alphabet, right? When we want to talk about a string, we have to say it's a string over an alphabet. So the question is, what alphabet could these strings be over? Well, there's an infinite number of alphabets it could actually be a string over, right? One is all English lowercase letters. One alphabet might be all of the symbols on the on your typewriter keyboard. Another might be all of the English lowercase letters plus all the numbers, all the individual digits from 0 to 9, plus all of the smiley faces you can think of. I'm going to remind you, you've been assigned a lot already, and I will continue to assign a bunch of practice problems from the book. I'm about to do some problems that don't have the answers in the back of the book to go over with you. I'm generally going to give you as homework problems that do have the answers in the back of the book, and I really encourage you to do them, and if you have problems with any of them, to ask me questions, because it's by doing the problems and practicing those problems that you're going to succeed in this class. So let's do some problems that don't have the answers in the back of the book together. So here's a problem which is page 54, problem 7, and we're asked to write down all possible strings of length 2 over the set ABC. So effectively, we just need to find all combinations of these letters that are of length 2, right? That have two letters in them. So here's what I've got. I recommend you come up with some methodical way when you're doing a problem like this to figure it out. So I kind of say, well, what are all the strings that start with A? There's AA, AB, AC. What are all the strings that start with B? Well, BA, BB, BC, and then all the strings that start with C, right? So that's how I did this one. We talk about string concatenation just like we do in programming. And we say we concatenate two strings by placing them together. So, for example, we could concatenate Obama and USA, or Rowan in the empty string, or Rowan and the smiley face. And it does exactly what you would expect. The only thing that you might want to note closely is anything concatenated with the empty string is just the original thing that you had. Okay, here's something I'm sure you did not guess, but we could use a list to represent a string. I'm sure you're thrilled, right? But yeah, so for example, if we talk about this string, behind the scenes, if we're trying to do this on the computer, we would probably represent it like this on a list, and we could use the head and tail operations on the list to access different parts of that list. And again, we'll represent lambda, the empty string, by the empty list. Okay, so let's now define a language. A language is defined to be a set of strings. And the fact that we don't say a finite set of strings is very important here. We've said an alphabet's a finite set of strings, and a string is a finite ordered sequence of 0 or more symbols, but a language can be of infinite length. Okay, here's some finite languages that I have. So for example, this set here is a language over the alphabet AB. Lambda, the set containing just the empty string, is certainly a language because a language is just a set of strings. Lambda is a string. So there you go. And it's a language over the alphabet AB and actually over any language, as we said before. This is a perfectly legitimate set of strings. It's also a language over the same alphabet AB. The empty set is indeed a language over the alphabet AB. I mean, the empty set is a set, right? It's a set of strings if you want to say it's a set of strings, so sure. The empty set is a language over the alphabet AB. And let me just be very careful here to point out that the empty set is not the same as the set containing lambda. This set here has one element. The set on the left has 0 elements. Yet another definition. If A is an alphabet, then A star is a special set, which is just defined to be the set of all strings over the alphabet A. So let's do an example. Suppose A is the set containing just two symbols, A and B. My first question for you is A star a language? And the truth is, you should be able to figure out this answer without knowing what's in A star, because what's the definition of a language? A language is a set of strings. And A star, by definition, is just a set of strings. So A star, definitely a language. How big is A star and what is A star? Well, let's think about what A star is. If we have this alphabet here, there's going to be an infinite number of strings over that alphabet, right? So here's the start of A star. A star always, A star contains lambda because, of course, lambda is a string over any alphabet. And then the way I kind of write out A star is I say, well, let me think, what are the strings of length 1? Well, there's 2 of them. What are the strings of length 2? Well, let me put an A before each of the strings of length 1, and then a B in front of each of the strings of length 1, and that gives me the strings of length 2, and then I can kind of repeat this to get the strings of length 3 and so on. Another definition, or you might want to call it notation, S to the N. If S is a symbol, then S to the N is just N copies of S. So, for example, if S is this smiley face, then S to the 0 is lambda, S squared is 2 of the smiley faces, S to the 4th is 4 of these smiley faces. Just as a reminder, the natural numbers for the purposes of our class will start at 0. You, of course, know the integers. And so we can use set notation to represent languages using the integers or the natural numbers also. So for example, if we have the set of all symbols a to the n such that n is in the natural numbers, right? We get lambda, right? A, right? This is all strings of length 0 or longer that contain just the symbol a. What about this one? A concatenated with b to the n, where n is a natural number. Think about it for 1 second. You may even want to pause the video here. I'm not going to give you long pauses, but I'll let you pause the video. So what have we got? Well, every string starts with an A and then it has 0 or more B's. Right? How about this one? The tricky question in this one is do the number of A's and B's have to match? And the answer is yes, because we have A to the n, B to the m, B to the n here, right? So we have the empty string, of course, and then all strings with 1A, 1B, 2A's, 2B's, and so on, in that order, right? Order is important here. A to the n, B to the m. Now notice that we're using two different symbols here. And so this is really all strings let's try again. This is all strings that start out with 0 or more A's and then have 0 or more B's. So all the A's come before the B's, but the number of A's and B's may be different, right? So again, when I'm trying to write this out, the easiest way for me to try and write this set out is to say, let me tell you the sets, the elements, the strings in here that are of length 0, then of length 1, and so on. And finally, this one, we've got A to the n, where n is in the natural numbers, and B to the n, and in the natural numbers, and we're taking the union of these two sets. So notice that we're never going to mix up the A's and the B's here, right? We're unioning the two sets, but we can take any number of A's and any number of B's. We'll also talk about taking the product of two languages. So if L and M are both languages, then the product of L and M is another language. So it's the language consisting of all the strings of the form ST, where S is a string in L and T is a string in M. The easy way to say this is it's all the strings where you take one string from L and one string from M and you concatenate them together, you squish them together. So suppose we have L and M as defined here, then you want to pause this video and just check, but I think you'll find that this is LM, right? So we take one thing from L, let's start with lambda, and go through all the elements of M. So lambda concatenated with A is just A, lambda concatenated with B is just B. Let's take the next element of L, concatenate that with everything, the next one, concatenate that, and you get this list. Excuse me, you get this set. Let's be precise, please. So here's a question for you. Does LM always equal ML for any pair of languages? So here's a pair of languages, and I've told you what LM is. So take a minute and figure out what ML is. Pause the video again. That's what I get for ML, and they don't look equal to me. So sure, we know that LM isn't always equal to ML for any pair of languages, but are there any circumstances where LM can equal ML? And again, pause the video, think for a minute. And, you know, I can come up with a couple. I think the easiest one is if L and M are the same thing, right? Then there's no problem. Slightly more tricky, if either L or M is the empty set, then LM is the same as ML. And similarly, if L or M is the set with just one string in it and that string is the empty string, then I think if you try it, you'll find that LM does indeed equal ML. Let's do another problem from the textbook. Here's one on page 54, problem 9. It says use your wits to solve each of the following language equations for the unknown language. And by use your wits, they just mean figure it out, think about it, and however you can figure it out, figure it out. And they're asking us to solve for L. So if you look at this, it says L times a set, right, is this set, and L times a set is this set. So they're just asking us solve for L. Okay, so here's the first one. When I take L and I take the product of L with the language, which is the set containing just the elements, the symbols A and B, here's our answer. So I figure looking at this, it's pretty clear to me that the size of L is going to be 2. And because I see A and B in this set, I know lambda's in there. So, because lambda times A is A and lambda times B is B. So I just got to figure out what else is in there. And in fact, if you push it through, you'll find out that L is the set containing lambda and BA. Here's the next one. We have L times the language containing the empty string and A, and we get this language. Notice that lambda is an element of the resulting language, which means that we're going to have a lambda in L so that we end up with a lambda here, right? Because lambda concatenated with lambda gives us lambda. So pause the video for a minute, figure out what you think is in here, and then restart. So there's what I get. Is that what you got? If not, do it again. Here's another one. Lambda, L, right? The language L, the product of the language L with this set gives us this stuff. And now I notice that lambda is indeed in this second set, in the second language, but I don't see it in the result, so I know lambda isn't going to be in my language L. There's what I get. And now let's talk about the product of a language with itself. So before we were talking about s to the power of n, so if s was a symbol, s to the n was n copies of s. Now we're talking about L to the n. So if L is a language, then L to the n is L multiplied by itself n times. And yet another special case, L to the 0th power, L superscript 0, is going to be the set containing just the string lambda. Let's try an example. Let's suppose L is the language that contains 2 strings, and we ask, what is L cubed? See if you can do this. Pause the video and then restart. So here's how I'd go about doing this. First, I'd figure out L squared. And to figure out L squared, I would take A and put it in front of each of the elements of L. And then I would take BB and I would put it in front of each of the elements of L. And this is what I get. And then I would figure out L cubed, right? L times L squared by taking A and putting it in front of all these elements, and then taking BB and putting it in front of everything in L squared. So here's my final answer for L cubed. Here's some questions that I'm calling trick questions. They're only really trick questions because I'm using some weird values for these sets. The truth is they're easy if you know your definitions. So if we define L, M, N, and P like this, the first question is, are L, M, and N all languages? Well, look at your language. What's a language? A language is just a set of strings. Well, L is a language because it's a set of strings. M is also a set of strings. It only has one string in it, and that string is the empty string, but it's still a set of strings, so it's still a language. And N, well, sure, it's a set. It's the empty set. There's nothing in it, but sure, that could be considered a set of strings. The next question, what is L, M, the product of the language L with the language M? Since the language M just contains the empty string, lambda, LM is just going to be the same as L, right? If we talk about Ln, the product of L and N, well, remember language product is take one thing from here and one thing from here and concatenate it. There is nothing in N, right? N is the empty set. So the product Ln produces the empty set. And what is M, the product of the language M with the language N? Well, again, anything, the product of anything with the empty set is going to be the empty set, because in order to compute the language product, you take one element out of this set and concatenate it with an element out of this set, and there's nothing in there. Finally, there's the question, what is p cubed? And this is a little bit trickier, right? But what I'm going to tell you is p cubed has 4 elements in it. P cubed has lambda in it, right? Because if we multiply lambda by itself 3 times, we get lambda, right? If we concatenate lambda with itself, I'm sorry. It has a, because that's the same as a concatenated with lambda and lambda. It has AA, because that's just AA lambda. And it has AAA if we take all 3 A's. So p cubed is the set containing lambda, A, AA, and AAA. Let's do another problem from the book, problem 8, page 54. So we're asked to allow L equal this, M equal this, and it says evaluate each of the following language expressions just to figure out what they are. So if we start with ML, we just need to take the language product of this set with this set, this language with this language, right? If you do it out, here's what I get. You should check my work. One of the things that I notice when I look at my set is that, in fact, I've got 2 copies of the string AB. Now, because of the way we're defining sets, that's fine. But to show that I really understand what's going on, I'm going to just get rid of 1 copy. So I show you, yeah, I know that a set doesn't have any duplicates, right? But strictly speaking, the way the book treats sets, the way we'll treat sets this semester, if you have AB written down twice, that's just exactly the same as this set on the bottom. And what about L to the first power? Well, L to the first power is just L, right? That's easy. Okay. Now we're going to talk about L star. So we're talking about the closure of a language now. Before we were talking about A star, where A was an alphabet, and A star is the set of all strings over an alphabet. Now we're going to talk about L star. So what happens when you star a language? And the answer is that the closure of a language, if you take L star, you just take the union of L0, union with L to the first power, union with L squared, union with L cubed, and so on. So, for example, if L is the language which consists of just the string A, and we ask what is L star, we get L to the 0, which is lambda, L to the 1, which is A, L squared, which is AA, and so on. Right? And by the way, it's interesting to note that that's the same as if I treat this as an alphabet, right? Then I get the same answer. Suppose L is the language A comma B. What's L star? Well, now we're taking the union of L0 with L1 with L squared and so on. And L1 is just going to be, L0 is going to be lambda. L1 is just L, so we union that in. L squared is the product of L and L. We get these guys, and so on. If L is just the language containing the single string lambda, then L star is also just the language containing just lambda. And if L is the empty set, what is L star? Well, now you need to think about this a little bit harder. So think for a second, pause the video. And the answer is that L star is actually the set containing lambda, because remember that L to the 0th power is always lambda for any language, and that's true even for the empty set, right? The language that has no strings. So kind of another trick question. Okay. We have talked about L star. Now we're going to talk about L plus, which we call the positive closure of a language. And L plus is just the same as L star, except we don't union in L to the 0, right? So we don't necessarily have a lambda in there. We may have a lambda if L has a lambda in it, but we don't guarantee to have a lambda the way we do in L star. So if L is the language with just the string A in it, then L star is the, then L plus is this language, right? There's no lambda. But if L is the language containing lambda and A, then L plus does indeed have lambda in it, right? Because L to the 1 includes lambda. If L is the language containing two strings A and B, there's L plus. And if L is the language containing just the string lambda, then L plus is the language just containing lambda. And if L is the language specified by the empty set, so the language consisting of no strings, L plus is also the empty set, right? Because L to the 1 is the empty set, L to the 2 is the empty set, L to the 3 is the empty set, and if we take the union of all of those, we still have the empty set. So now I'm just going to list several properties of closure that I got straight out of the book. And your job is just to make sure that they make sense to you, right? Look at them and say, yeah, I kind of believe that. You don't actually have to prove them all, but I just want you to say that in your gut you kind of get it. So the first two actually are ones we've talked about before. So if we have the language which just consists of the empty string, then if we star that language, we still just get a language with the empty string. The other one is that if we take the star of the empty set, the only element in that language is lambda. That's what we've talked about already. Here's kind of an interesting one. We know that lambda is an element of L if and only if L plus equals L star. It's if and only if, so in order to prove it, we need to say if this, then this, and also if this, then this. And you can do that. You can convince yourself pretty quickly. I'll give a very informal explanation here. We know that if lambda's in L, then lambda's definitely in L plus, right? Because lambda is in L1, and that's part of L plus. And so since the difference between L star and L plus is only the potential absence of a lambda, we're good. Similarly, if we know L plus equals L star, then we know lambda's in L plus. And the only way we could have gotten an L lambda inside of L plus was if it was in L. These last two actually are a little bit harder to see. They kind of have to do with, once you've got an infinite set, your infinite set can't really get any bigger, or you just have the set containing just lambda, in which case it's pretty easy. Try these out where L equals lambda, and then try them out again just where L equals maybe the set containing just two elements, A and B. And you should be able to convince yourself that at least for those examples, these statements are true. And then, I'm not going to have you do a formal proof of this. I just want you to kind of believe this and understand this in case I want to use it later. Okay. Here's some more properties of closure. If L and M are both languages, then if we take L star, M star, and star the whole quantity, that's the same as L union M star. Again, try and just convince yourself of this. A way to do that is maybe let L equal the set containing just A, and let M equal the set containing just B, and try and push it out and see that at least for that particular case of L and M, this is true. And that might give you a feel for why it's true for any L and M. Here's another kind of weird one. And again, just try L is the set containing just A, M is the set containing just B, and push through a little bit and see if you can convince yourself that this is true. At least for that example, of course. You're not proving it, but you're showing it's true for one example, and that may give you some intuition as to why this is actually true all the time. And same thing here. Just try it again, and you'll kind of see what's going on. Let's do another problem from the book. This is problem 10 from page 54. So if L and M are two languages, and this is saying for each of the following languages, describe the general structure of a string X by writing it as a concatenation of strings that are either in L or in M. So it's basically saying if you have a string that is in your language, tell me what the string looks like. So for the language LM star, I might informally say, well, X is either a string in L or it's a string in L concatenated with one or more strings from M, right? So either, since we've got M star here, and M star includes lambda, this could just be L concatenated, well, a string from L concatenated with lambda, so that gives us just X as an element of L, right? Here's the more formal way of doing it. Or we've got L plus one or more things from M, right? So either X is an element of L, or X is some string where the first part of the string is in L and all the other parts are elements of M. Here's another one. What's the structure of a string where we have L intersected with M and then we take the star of that? And of course, the answer of that, it's almost easier to look at the formal definition. Well, L intersect M might be the empty set, right? It might have something in it. Regardless, when we take the star of anything, we know that lambda's in there. And if there is if there are any elements that are in the intersection of L and M, then we just have X takes the form of a bunch of strings concatenated together where each of those strings is an element of that intersection. One more, if we take LM star, right? Again, of course, we know that lambda has to be one of the options, right? So either X is the same as lambda, right? Because lambda is definitely an LM star. Another thing that we know is that if M has lambda in it, X could just be something in L. If L has lambda in it, X could just be something in M, right? Or else X is some combination of elements from L and elements from M, right? Okay. Another problem, problem 11, just asking us, try to describe what does this language look like? So look at this set for a minute, right? So we've got the set of all strings. This is all strings that are either lambda or have an A or a B in them, right? And we're subtracting off all the strings, well, we're subtracting off lambda and all the other strings that have a B in them, right? So effectively what we've got is all of the strings over the alphabet AB that have at least one A, because if they were all B's, we got rid of them from our set.